Hello world, my name is Victor Engelmann, welcome back to my channel. Today I want to do something relatively simple. I just want to look into the directory /proc in Linux systems. And yeah, you can already see there's a lot of stuff here if you look at my screen, and all this stuff, what is this, right? I mean, you may have heard of /proc and you may have a rough understanding what it does. So here you have these directories with these numbers for names, and you probably have heard that these directories correspond to the processes running on the machine. Right, so here we have the process ID 828, and that's the same as the directory name here in proc 828. And yes, there's a lot of stuff in here, and let's look around in this directory and see what we can find here. First of all, what is proc? The mtab is a list of mounted file systems, and in here we have proc, sys and dev. These are virtual file systems, so they don't talk to some actual hard drive, no block device in the background where they map some directory structure and files to physical addresses on the block device, you know, like here dev SDA4, which is mounted on home, is an ext4 file system, right? So you have a file system handler for ext4, which talks to this block device, SDA4, whenever you look into the home directory. And when you look into the proc directory, then this is not talking to any actual block device in the background. The handler for that directory, proc, the proc file system is a virtual file system, which when you ask it, hey, give me the list of directories in /proc, then it will talk to the kernel and ask it, hey, give me a list of processes, and then it will give you a list of the process IDs instead of directories. But it will communicate with the file, pretending to be a file system. So this will look like directories and files, so that in your bash scripts you can iterate through that stuff and read information from these virtual files you find in there. And now let's look what we can find in there. Okay, again we have all these directories corresponding to the different processes, right? So if we go back to 828, that was system D. Right. Here system D is process ID 828. So let's look into that directory. Okay, some things that we find here. We have here a file named cmd line, and if we read this file, it tells us the command that was used to start this process. So what we see here is first the binary user lib systemd systemd, and then
--user is the parameter. We don't see a space here in between, but yeah, if you hex dump this output, then you will see that there is a null character between the binary and the parameters, and yeah, the shell just doesn't print them because null characters aren't printable.
Okay, then what else can we find here? We have some symlinks here, these blinking things, and it tells me, it cannot tell me where these symlinks are pointing because I don't have the access rights. So let's run this as root again. Okay, and now it gives us the symlinks, and yeah, CWD, current working directory, is yeah, a symlink to the directory from where the program was started. Okay, so when you are in a shell, for example, and you move that shell to a certain directory, then you can execute programs from within that directory, you know, with dot slash and the program name. But you don't have to. You can just input a directory relative to the directory where you are currently at. Or you can use an absolute directory. And this CWD, current working directory, tells you where has this shell been when it started the process. The exe is an executable binary. In my opinion, this should be called bin and not exe. I mean, this isn't Windows, right? In Linux, we call our executable files binaries and not executables. So yeah, but yeah, this is a link to the binary file that is running. Then here we have environ, which okay, I don't have access permissions. So this gives you the all the environment variables that are present for this process. Yeah, some stuff that we see in these environment variables is, for example, here my username, WYOOS, right, the same that you see here. My system is configured to use German UTF-8 encoding. You have the path variable in here, which tells your shell where to look for binaries when you input a command. Here's a home directory of the current user, the shell, the default shell of the current user. Okay, the next thing you find here is a directory fd for file descriptors, and this again has a lot of IDs, right? And 0 is standard in, then 1 is standard out, which is piped to a socket, and 2 is standard error, is also piped to a socket. Yeah, and systemd uses some more file descriptor IDs. So yeah, this directory proc process ID fd tells you or gives you symlinks to the files that the process is talking to, has requested access to. Yeah. Okay, now let's have a little bit of fun here. I will just run some program, and I will just use the sleep command, which does nothing for 10 minutes. When I pass it 600 seconds as a parameter, and I will send it to the background so that I'm told the process ID. Okay. Now, we had this proc, then the process ID. So now I'm dealing with this sleep command. Right? If I cat its command line, I get sleep 600. Right? That makes sense. And yeah, now let's mess with its file descriptors. Remember, file descriptor 1 is standard out. So you know what, let's look at the file descriptors first manually. So 1 is a symlink to dev pts3, which, well, will be the TTY of this bash instance here. So actually let's figure this out. This should actually work. Okay, the process ID of this bash instance is 9182. So let's look at the file descriptors for that. And look at that. I was completely right. The bash, this bash here, has the same TTY, or pseudo teletype actually, number 3, to which its standard out is going. So yeah, now let's write something to that process's standard out. Okay. And look at that. Our message hello world has appeared here in this bash, or in this TTY, which also runs this bash. Then in fd info, you have small files for each of these file descriptors. And let's look at file descriptor 1. This tells us the offset where the file descriptor is, to which the file descriptor is moved. So where in the current file you would write if you would write something to standard out here. Then some flags. This I think is the inode. And okay, mount ID, I don't know what that is. Okay, the next thing is proc process ID maps. And this gives us a very interesting list here. The first column tells us a a location within the address space of the program, and then a file over here. Okay, and this here is an offset within that file, and this is an information about the hard drive where this is coming from. The thing that this tells us is user space programs can ask the kernel to memory map a file, and then you can so then from the perspective of the user space program, it looks like the entire file is now inside your address space. It actually isn't. The kernel is doing some magic to pretend that this was the case. So the kernel will allocate a certain space within your address space, and when you try to read the data from some page within that memory range, then on first try the data won't be there. That will cause a page fault, which is a kind of an interrupt, and the interrupt handler for that will then read the data from that file, put it into this part of your address space, and then will continue running your program. Okay, so when you access the data, it is then read on demand from the file, and then you can just iterate through the file as if it was completely in your address space. So I think that is quite interesting, that you can do stuff, and the kernel uses this functionality also to I don't think it's the kernel per se that does that, but it's a dynamic linker, which loads the libraries that your program is linked against into your process's address space. So that is part of how you can execute code from other libraries. And one interesting part is that these libraries can be shared between different processes. So when you load the libc, for example, and you have 100 programs that are linked against the libc, then it will actually only be loaded once into memory, and all the programs that access it will just use the same memory for that. I think that's really smart and also good for performance. Okay. There is also mem, but that is only there for ptrace. So that is for debugging purposes. Now the entry root here is another symlink. In this case, it points to the root directory, and this is for cases where you run something in a change root environment. You know, where you want to isolate a process so that from the perspective of the process, it looks like everything outside of a certain directory it doesn't exist. Okay, so for that process, it looks like the directory you use for your change root was the root directory. The subdirectory task would give you a list of threads started by this process. So this program only has a main thread, and then you can look into that thread. It has its own stack. It can have its own file descriptors. these I think are the child processes. So the processes that were started by this thread. With proc process ID stack, you can look at the current stack of the process. I think that's very interesting. Status gives you a lot of information about the status of the program, its name, its file creation mask, so the some bits that are forced to be off when you create files. Okay, the state here is sleeping, process ID 828.
PPID is the process ID of the parent process, you know, the one that started this process. And here we have ppid1, so yeah, this systemd was started by the init process.
This here I think is a task group ID. The UID of the user who started it, I think. Group ID. Some infos about the memory usage. Shared memory here. One thread. Okay. That was the status file. And there's also stat, which I think is the same stuff we have in a more bash friendly way. And stat_m. I don't know what stat_m does, so let's look into the official documentation for this on kernel.org. Here docs.kernel.org/filesystems/proc.html. I've looked into a lot of resources about the proc file system, and honestly this is the only one that I've found really good. So here let's look stat_m process memory status information. Process status in human readable form was the first thing that we looked at, and stat is process status. Okay, another thing that I want to talk about is this entry here, self. Proc self is an interesting directory. It's actually a symlink, as you can see here, and right now this points to 8862. So 8862, right? If I run this again, it now points to 8866. So this won't be consistent. And if we try to read this to find out, for example, what program is it running? Well, it's telling me cut proc self command line, so it's giving me this exact line. Well, not exact, there's a space missing, but the point is that proc self, whenever you dereference it, it actually replaces it resolves to a symlink on demand for the processor that is currently trying to access proc self. Okay, so when I run ls, and ls is looking at the directory self, then the kernel or the procfs backend will tell ls that self points to 8866, which is the process ID of this ls command itself, right? And if I run ls again, then that other ls command has a different process ID. That's why I get a different PID here. And if I try to read that, then resolving proc self resolves to the process ID of this cat program, and that is why then cat is presented with its own command line, right? So yeah, dealing with this self symlink can be a bit confusing, let's say. Yeah, but whatever. Okay, now let's look at some other stuff we find in proc. The thing is, proc is older than the sys file system, and back in the day, people put stuff into proc that, from today's point of view, doesn't belong in proc. And proc just became bigger and bigger and bigger until people realized, okay, this makes no sense anymore. We need to split a separate file system out from this, and that has become the sys file system. You know, the thing you find here, right, where you have your buses and your devices and modules, power stuff. You can talk to the kernel through that, the block devices. A lot of stuff that belongs in sys has been in proc before, and for backwards compatibility, it is still kind of maintained in proc. Although often proc will only have a symlink to the correct location in sys. Okay, but okay, let's look around in through some of that stuff. Okay, so for example, we have proc config.gz. When you build your kernel, then you're using your config file, right? We've discussed that in the video about building the Linux kernel. And when you build your kernel, then a copy of that config file is put into the binary of the kernel, but it is zipped. So with zcat I can unzip it. Okay, and so now here you can see all the config options that have been used in building the current kernel. And I think that's really useful when you want to build a kernel that you want to be similar, very similar to the current kernel you have right now. Then you can just take this config file and do some changes to that config file that you want to build, and then you basically have the same kernel as before, just with your few changes here. Okay. Proc file systems is a list of supported file systems. Here we have sysfs, you have proc, devtempfs is the file system that's mounted on /dev, which gives you access to the device files. config fs, I don't know what that is. A lot of file systems that I don't even know and that sound useful. I should look into these. And yeah, down here we have ext2, ext3, ext4 and vfat. Typical file systems. Proc cmd line gives you the command line for the kernel. Right, proc process ID command line is the command line of a process, and proc command line without a process ID in between gives you the command line of the kernel. Proc CPU info gives you informations about your processor, about all the processor cores actually. Proc interrupts gives you a list of system interrupts. Let me reduce the font size. Okay, here you have the different interrupt IDs, which I've talked about in the video about interrupts. These are the different handlers attached to the interrupts, and this list over here tells you which CPU core has handled which interrupt how often. Okay, a lot of times it makes sense to bind an interrupt to a specific CPU to prevent loading data from memory to different CPUs when it's probably already there in one CPU. Okay, here NVMe, that's an interrupt that obviously listens to my hard drive, my SSD hard drive. I think i915 has something to do with audio. ENP2S0 is my network device. And look, the interrupt has never been run because I haven't had this attached to a wired network since I've booted this. I only have it connected to Wi-Fi currently. SND, HDA, Intel, also sound. PCI stuff. XHCI and AHCI, I think, have something to do with hard drives. RTC is a real-time clock. Okay, whatever. Proc version gives you the kernel version currently running and some additional information about how it has been built. This one has been built with GCC. The linker that was used, and this was built on Friday, May 9th at 10:53. Okay. Proc k message gives you a list of kernel messages. I think that's pretty much the same you get with D message.
These are the same messages.
I think reading it once probably empties the file, so it's probably a FIFO, so we've read it, so now it's empty. Okay, syms. is a symbol table. Okay, maybe the kernel has been compiled with a config option that disables this functionality. Maybe, I don't know. This should give you a symbol table for all the symbols in the kernel. Okay, I don't know. Let's move on. Proc mem info gives you a lot of infos about the memory. Proc modules is a list of the loaded modules. And proc mounts is like the mtab, a list of file systems that are currently mounted. Okay, now let's look into procnet. And if you ask me, I think this is another candidate for something that should be moved into a different virtual file system, because I don't think this actually belongs in proc either. I think we need something like netfs or something, which should then do the stuff that currently is in procnet. Okay, some stuff that we find in here is ARP, which is the ARP table. This is just the router for this for my virtual LAN 31 that this machine is currently in, my VLAN. Hardware type flags. This address, this is a MAC address for this IP address, right? The ARP table stores information about which IP address has which MAC address, right? Net dev gives you some statistics about the devices, your network devices. Right, my wired network has no packets sent or received because my wired network has not been connected since I've booted this machine. But through my wireless device I have received this many bytes, and they were in this many packets, and it has transmitted this many bytes in this many packets. Okay, so that's some device statistics that you find in procnet dev. In procnet dev mcast, you find a list of multicast groups that these devices are configured to receive. So if you get a data packet for a multicast group, multicasts are broadcast to the entire network, right? But the interface then gets all these broadcasted messages, looks at the multicast group and says, no, this is not a multicast group that I'm configured to listen to, right? I'm only configured to listen to these multicast groups, so I will discard this packet, right? And only the multicast groups that you find in this list, only these multicast groups will be received and then handled. Okay, next thing, procnet IP underscore mask with a Q. Apparently doesn't exist because, I don't know, I think it's because the machine is not configured to do any masquerading. if you were doing some masquerading like I'm doing on my firewall, for example, then this would give you a list of the masquerading entries. You receive packets, change the IP address, and then send the packet on to that different address. And this table IP mask would tell you which IP is replaced by which other IP, right? Okay. Proc net stat. Holy cow, I have no idea. I think this is a list where I think these are the column heads, and these are then the data for these columns. Proc net root is your routing table. So your network mask 00000 means that absolutely everything is forwarded to your gateway, and 0A is 10, right? If you remember, I had right, this is my router, right? 10, 1, 31, 254. 10 is 0A in hexadecimal, so 10, 1, 31 in hexadecimal, and FE is 254 in hexadecimal, right? So all IP addresses with this net mask are forwarded to this gateway, and 10, 1, 31, right? The IP range for my own current VLAN with this mask, so stuff that matches this 10, 1, 31 is not forwarded to a gateway. This is sent directly through the network interface itself. Then you have some stuff for TCP. UDP, some statistics, TCP6, so, and UDP6, do we also have IP? Doesn't look like it. Okay, anyways, finally, SNMP. Okay, it doesn't exist. I've read about SNMP also existing here, but apparently it doesn't. I've misspelled it as SNMP. Yes. This is some info about Simple Network Management Protocol, which is a rather useful protocol when you are managing a network. Through SNMP you can talk to routers and switches in a very low level way, it allows you to configure the router in a very low level way, right? You just send a certain packet. I think it's even just UDP. A UDP packet which tells the router, hey, turn off your network port number 5, for example, or turn on network port number 5. This of course can be password protected, but it's not really secure, so it's generally advised not to use it. But I think SNMP3 has more security now. But I personally just find it too useful to not use, at least in a large network. In my home network, I'm not using it. If I want to configure something, well, I go directly to the device. But with SNMP, you can consolidate the management of all your devices in one place. Whatever, I don't want to go too deep into SNMP right now. But I think this is a pretty good selection of things that you find in proc. I think that's useful. And once again, if you want to know more about proc, the only thing I can advise you really to use is the official documentation on kernel.org. Again, docs.kernel.org/filesystems/proc.html. That's the official documentation for this. And here you find, really good infos about everything you find. And Okay, that's all I wanted to show you today. If you liked this video, like it, share it, subscribe, and see you next time.